So, hello everyone. Welcome to a new week. First lesson of the week, we're going to finish off taking derivatives of exponential and logarithmic functions. In the first video, what I'm going to go through is how we take the derivative of any exponential function with any base at all instead of just the natural exponential function. And in the second video, I'll finish the note off and we'll go through how we take the derivative of any logarithmic function, not just a natural logarithmic function. So the first part I have written out already is just our theory. Again, if I look at any exponential function with any base, here I've given an example, base 4. But if we consider this function in general with any base, say base b, a few restrictions on that base, how would I take the derivative of that? So to develop a derivative rule for this, what I've done is taken the ln of both sides. Remember that ln is just a logarithm, so we have a nice rule with logarithms that says if I take the log of a power, I can take the exponent and I can write it as a coefficient out front. If I now take the derivative of this here, I can take the derivative of ln y, which would be 1 over y dy by dx. It's our ln rule, and since I'm taking the derivative of y, we have to add on this dy by dx using our chain rule. And if I take the derivative of the right-hand side, keep in mind that ln b is just a constant, so my only variable is the x. So as I take the derivative of that, the derivative of x would be 1 times ln b, or just a ln b. Isolating for our dy by dx, I would multiply by y, and then from our original expression, we know that y is the same as b at x. So our derivative here then is b at x ln b. What we should notice is this is almost the same rule that we use when we take the derivative of our natural exponential function, and that is that the derivative is the exact same as the original function, except the added part here. If this is not e, then we also have to multiply by ln of whatever the base is, or ln b. So in general, I've written out our rule here it is, and the note just refers back to our natural exponential function, the idea that this rule in general also works here, that if I take the derivative of this using this rule, the derivative of e to the x would be e to the x ln of the base, so e to the x ln e, since e is our base, and the ln of e is 1, and that's where that specific rule comes for our natural exponential function, that it's the exact same rule, except for we have this ln of the base here. So I have a few examples here to take a look at that I'll work through just so you can see how this works. So if I want to take the derivative then of y equals 4 to the exponent x, then we would say y prime equals, with any exponential function, the derivative is just itself. And then we have to follow that with the ln of the base, which in this case is 4. And then we would still take the derivative of the exponent, in this case the derivative of x is 1, so that's it. We're done. In the second one, f prime at x equals, again, if I have an exponential function, the derivative of an exponential function is just itself, multiplied by the ln of the base. In this case, that would be ln 5. So that's the derivative of the outer function, the exponential function, and then I still need to take the derivative of the inner function, or our exponent, which in this case will give us 2x minus 2. And there's our derivative. There's not really a lot of simplifying we can do with that in this case, so in this example I'm just going to leave the answer as is. The last one I want to do with you then just combines this with some of our other rules. Notice that this again is a product of two functions. Okay, we have the x squared and we have this exponential function, so we will have to use our product rule here. So f prime at x equals derivative of the first is 2x times the second function for x to the exponent x squared plus our first function x squared times the derivative of the second. Again, this is our exponential function rule, so we now have 4 to the exponent x squared multiplied by ln of the base, and then multiplied by the derivative of the inner function, which is our exponent, giving us 2x. In this case, because we have two terms, we could try to simplify here a little bit. I'm looking for common factors between these two. We should notice that 2x is common, 4 to the exponent x squared is common. So if I common factor those out, here I would be left with 1 plus, and here I'm left with an x squared and a ln 4. So there is our derivative using our product rule combined with our exponential rule, and then a little bit of simplifying at the end. In general, if I had something like this here, it's not completely general. I've picked the base of 5, but if we have something where now we have any base that we want and some function in the exponent, again, this is our chain rule. So for our derivative f prime at x, we would get then the exponential function over again, multiplied by ln of the base, in this case ln 5, and then I would have to take the derivative of the inner function, so the derivative of the exponent, so multiplied by g prime at x. So there's sort of our general scenario for how we take the derivatives of these exponential functions. In the second video then, I'll run through similar idea, how do we take the derivative of any general logarithmic function.